In this lesson segment, we're going to introduce and explore the concepts of area and perimeter as they apply to a few basic shapes, like triangles, circles, and quadrilaterals, which include squares, rectangles, trapezoids, and the like. So with that, let's begin. What is area? Area is the measure of the size of a surface. So if I took one of the triangles and I shaded in everything in the middle, that shaded region would be essentially the measure of my area of the surface. Perimeter is a length. It's the length I would travel if I started at one point on the outside of my shape, traveled all the way around the outside of that shape back to the same point. That measure of distance would be my perimeter. So for the triangle shown on top, labeled equilateral, I could label each side A, B, and C. The sum of the lengths A plus B plus C would be the distance I traveled around the shape, otherwise known as the perimeter. Let's take a quick look at the different types of triangles. The first one is equilateral. That means all side lengths are the same, as indicated by the hash marks on each side. The next triangle is the scalene triangle, where none of the sides are equal. The right triangle is indicated by the little square symbol in the corner, and that indicates that it's a 90-degree or right angle in the triangle, thus the name right triangle. An isosceles triangle has two sides only that are congruent, indicated by the hash marks on the two sides. The measure of the size of the surface, that is the area of the triangle, is 1/2 base times height. And that can best be seen from the right triangle, whereas if I create the mirror image of it with the dashed line shown, we can see that it forms a rectangle whose area is length times width. And the two triangles of equal side are essentially half that area of length times width. So in other words, they're 1/2 length times width, where in this case I'm really calling my width and my length my base and my height. So it's 1/2 base times height for the area of a triangle. Let's calculate the area of a scalene triangle where none of the side lengths are equal. Suppose I had the base equal to 10 units and my perpendicular height equal to 5 units. My area would be 1/2 10 times 5, or 1/2 of 50, equals 25 square units. Area is always in square units. Let's further suppose the other two sides of my scalene triangle are of length 15 units and length 6 units. I can calculate the perimeter by adding up all three sides. It's going to be 10 plus 15 plus 6. That totals 31 units for the perimeter of the scalene triangle. What's the area of the following triangles shown, A and B? The student might look at it and say, well, it's base 5, its height 7, therefore it's 1/2 5 times 7, or 1/2 of 35. That is not correct, because that length 7 is not your height. It's not the height perpendicular to the base. We cannot calculate the area without the height, but let's suppose we were given another area, the area of triangle A. We could use that information to derive our height. So for example, if the area of triangle A is 15 units squared, I know the base of triangle A is 3 units. So 15 area equals 1/2 base times 3 times my height, which we'll denote by the variable h. Solving for h equals 2/3 15, which equals 10 units. In the absence of having an actual height perpendicular to the base, I was able to derive it by noting the area of one triangle would allow me to calculate the height, the very same height of the entire larger triangle AB. From that height, I can then calculate the area of my larger triangle AB. Given that the base is 3 plus 2 or 5, I know the area of my triangle AB now is 1/2 times 5 times my vertical height of 10, which is 1/2 of 50, or 25 units squared. Noticing an indirect way to get at the information or derive the information you need is very important for the exam. You'll see that on a lot of problems. Let's look at four-sided shapes called quadrilaterals. Two you're probably very familiar with, rectangles and squares. In addition, they include rhombuses, parallelograms, trapezoids, and more. Like triangles, the perimeter is going to be the sum of the side lengths. In this case, there are 4 side lengths, however. The perimeter is going to be A plus B plus C plus D, given the 4 different side lengths. And in the case of a square, all the side lengths are equal. So we know A equals B equals C equals D. So my perimeter is just going to be 4 times S. And my area in that case is going to be one side length times the other, S times S, or S squared. The rectangle has 2 sets of equal or congruent side lengths, as indicated by the orange and purple hash marks. I could call these 2 sides a length and a width, L and W. The area of that rectangle is L times W. In addition, we have a parallelogram, which has 2 congruent side lengths, just like the rectangle, but they're not perpendicular in this case. So if I label my sides A and B, in the case of a parallelogram, to calculate my area, I still have to, much like a triangle, find the perpendicular height h, because the area of my parallelogram will be my base, B, times the height, h. For the trapezoid, we again have to use that vertical height and multiply it by the 2 different length bases on top and bottom. So the formula is 1/2 B1 plus B2 times h. If you think about it, for the trapezoid, you're calculating the area of a rectangle, where the length is really the average of B1 plus B2. The approach for all of them is similar. It's side times side. It's just the execution of the details that differs.
For our next shape group, let's look at circles and the area and perimeters of circles. Well, actually, in the case of perimeter of a circle, we call it the circumference. And if we look at the 2 circles shown, we'll see a circle is essentially a shape with equidistant points from the center of the circle. They're all r, or the radius as we call it, away from the center point of the circle. And the diameter shown in the second circle is a line or a chord entirely across the circle through the center. And it's essentially 2 times the radius. So we can look at the diameter as twice the radius. So let's take a look at the area and the perimeter. The area of a circle is pi r squared, where pi is this number 3.14159, which we can approximate with 22/7 for purposes of the exam. That will help you do calculations with fractions and potentially cancel and simplify expressions. So let's look at a particular example of the area. Suppose we had a radius of 5 units. Our area would be pi times 5 squared, or 25 pi square units. What would the perimeter or circumference of our circle be in that case? It would be 2 pi r, which would be 2 pi, and that's the number of times our radius goes around a circle, which is approximately 6, or just more than 6. In the case where the radius is 5, that's 2 pi times 5, or 10 pi units for our circumference to go around the circle. We could also express the circumference as just pi times the diameter, knowing that the diameter itself is 2 times r. That covers the basics of area and perimeter for a few common shapes. However, on the real exam, you're going to have to combine shapes and add them together or subtract them to figure out what different shaded areas are, so it has a new or different layer of complexity. In the upper left, we've got a quadrilateral with a semicircle or a half circle on top. That semicircle is radius 2, so actually I know the side of my quadrilateral on the top is 2 plus 2. It's 2 times the radius or the diameter of the circle, so it's 4. We're given that the side of the quadrilateral is 4, so this must be a square, a 4 by 4 square. And the area of a 4 by 4 square is 4 squared, or 16 square units. The area of my semicircle is going to be half the area of the circle, which is pi r squared, or pi times 2 squared. So 4 pi over 2 is 2 pi. So the area of my combined shape is going to be 16 plus 2 pi. The next upside down L shape in the upper right corner has only horizontal and vertical lines. I can deduce what some of the missing line segment lengths are. If I know the left side is of height 6 and the right side is of height 4, that means the difference, the other side on the right, must be 2. It's 6 minus 4. Likewise, if 5 is the length of my top side and 3 is the given length of the bottom side, the missing bottom side must be 2 as well. So now I can actually look at this as a combination of a rectangle and a square. I have a 6 by 3 rectangle, so the area is my length times my width, or 6 times 3 for that larger rectangle. And the area of my smaller square is 2 by 2, which is an area of 2 times 2, or 2 squared, which is 4 square units. And I sum the area of my rectangle and my square to get the final shaded shape area result. And that's 18 plus 4 equals 22 square units. Unlike the last two problems where we added different shapes together, in this case we have to subtract one shape from another to get our net area of the gray shaded area. So in the lower left we've got two rectangles, a 6 by 4 outer rectangle and a 2 by 3 smaller rectangle that appears to have been cut out from within the larger rectangle. So in general, when we have to look at subtracting shapes, we take the area of the outer shape and subtract the area of the inner shape. So the area of our outer shape in this case is the large rectangle, it's 6 by 4, so length times width is the area, and that's going to be 24 square units. I'm going to subtract from that the 2 by 3 rectangle of length times width 3 times 2, which is 6. So my result will be 24 minus 6 equals 18 square units, and that is the area of the gray shaded region shown. Our last example in the lower right corner is a lot more interesting. It's a triangle with an inscribed circle. So again, our approach is going to be to find the area of the outer shape minus the area of the inner shape that's been cut out. The area of the outer shape in this case will be a triangle. And we need the base, that's given, of 15 units, and the perpendicular height of 12 units. So my area will be 1/2 15 times my perpendicular height of 12, which is 1/2 of 180. The area of my circle I can calculate because I'm given the radius of the circle, and the area is pi r squared, or in this case that'll be pi times 4 squared. So in total, my shaded gray area will be an area of 90 minus 16 pi square units, the area of my big triangle minus the cutout area of the circle. And many problems will present themselves like this. So as we learned the basic shapes and how to calculate areas and perimeters, now we can add the complexities we'll see in real problems of adding and subtracting different shapes.